ko buka fendi mo la an tawra ba do sam
bara ke ku folo ajibe lori nya labi tamete mingi mun na re
teku
bari ko do famo ke
imagine nani nyambol si zol le keje kisigi man si zol no le kabun ka nyoma bari nyambu kilo ni manya na kafindi ni nambe ko zol la ga
ngale limbeta de be nyambo do dilanna
nyara ni ko rim fennat nyara nata
bari famo kada
nata bungono tammi bungono nyara ngando ko fele ko kede bar nganda ni pelo la ndija
iyo awa la
bungono bismillah bisu diara
pendulala yefu ngotanka sina dulutanka koro korota korota.
Hi everyone, my name is Mr. Babukar Aw, your chemistry tutor. And today, our topic of discussion will be the last aspect of thermochemistry that we will be discussing in this course. And that is standard enthalpy of neutralization. But before this, we will try and answer the assessment questions we gave the last time. And then let's try and answer these questions together. And the assessment question reads, 4.0 grams of ammonium trioxynitrate 5, which is NH4NO3, is dissolved completely in 100 cm³ of water in an insulated container. The temperature falls from 23 degrees Celsius to 70 degrees Celsius. Calculate the enthalpy of solution of ammonium trioxynitrate 5. And then we are given a clue, and the clue reads hydrogen equals to 1, nitrogen equals to 14, oxygen 16, and finally the specific heat capacity, which is C, is equal to 4.2 joules per gram per Kelvin. Now, the first thing to calculate in this question is the change in what? In temperature. That is the difference between the initial temperature and the final temperature. Change in temperature. And here, the initial temperature is more than the what? Final temperature. Which means when we are calculating the change in temperature, in this case, we will say 23 minus 17. The difference between 23 and 17 is 6. Now we will have 6 degrees Celsius as our what? Change in temperature. Now you can see the temperature on the clue is per Kelvin, and I'm still maintaining what? The degrees Celsius. I'm maintaining this degrees Celsius because even though you convert this into Kelvin, and then you find the difference, you will still have what? 6 Kelvins. And 6 Kelvin is the same as this 6 degrees Celsius in this case, because we are just finding the difference. Now, after finding the difference, we calculate what? The heat involved. I'll calculate here the heat what? Involved. Not the heat evolved in this case, but the heat what? Involved. Now, the heat involved here is calculated by mc theta. Again, the m is the mass of the water used, the c is the specific heat capacity of water, and theta is the change in temperature. And according to the question, 100 cm³ of water was used. And here we have what? Mass. But we know that 1 gram is equivalent to what? 1 cm³. So therefore, if you have 100 grams, it will be the same as 100 what? cm³. So if we are given the water in form of volume, so therefore it is the same as what? 100 grams. So here we can say 100 times. The specific capacity of water given is 4.2. So we say 4.2 times, and the change in temperature is 6. So therefore we'll have 100 times 4.2 times 6, and then we will have 2520 joules. This is the amount of heat involved in this reaction, and this amount of heat was produced by 4 grams of ammonium trioxonitrate 5, and this 4 grams of ammonium trioxonitrate 5 is not equivalent to what? 1 mole of ammonium trioxonitrate. So therefore we calculate the standard enthalpy of solution in this reaction. Then we will say if 4.0 grams of ammonium trioxonitrate produces 2520 joules of heat. Therefore, 1 mole of ammonium trioxonitrate will produce what? And 1 mole of ammonium trioxonitrate is equivalent to what? We calculate the mass now. That is using the clue given in the question. Now we said nitrogen is equal to 14. We have 14 times 1 because we have 1 atom of nitrogen. Plus hydrogen is 1 times 4. That is the 4 atoms of hydrogen. Plus we again have nitrogen again, which is supposed to be 14 times 1. Plus we have oxygen, which is going to be 16 times 3. Now here we'll have 14. Here we'll have plus. Here we'll have 4. And here we'll have 14. And here we will have 46. So now we will say 14 plus 4 plus 14. Here we have 14 plus 46, and then we will have 78 grams per mole of ammonium trioxonitrate. And this means in every 1 mole of ammonium trioxonitrate you have 78 what? Grams. Now here the 1 mole of ammonium trioxonitrate will be what? 78 grams of ammonium trioxonitrate will produce X joules. We cross multiply from this end, and then we will have 78 times 2520 is equals to 4.0 times X. We make X the certificate formula by what? Dividing by 4.0, and this side also 4.0, and this will cancel each other. Now we'll have X will be 78 times 2520 divided by 4.0, and then we will have 49140, and then our unit will be what? Joules. But we can divide by what? 1000 again, so that we will reduce the value, and then we'll have here kilojoules. That is, the point is here we'll have 1, 2, 3, and then we will have 49.1 kilojoules. Now we come back to the initial and final temperature. The initial temperature is 23 and the final temperature is what? Is 17. In this case, as the reaction is proceeding, you see the system is getting what? Cooler, which means the temperature is going down. As a result, we will say, we will put what? Positive, we'll have positive 49.1 kilojoules. Now this positive now will tell us our system is cool because it is what? Endothermic reactions. And that's all about the assignment. And then we move to our main topic of discussion. Today we will be discussing about standard enthalpy of neutralization. As we all know what is meant by neutralization reaction. But in this case, we will be discussing about the enthalpy, that is the heat change that is involved in neutralization reactions. Now, this is the heat released when 1 mole of an acid, that is hydrogen ion from the acid, is neutralized by an alkali, and that is hydroxyl ion from the alkali or the base to produce 1 mole of water at 298 Kelvin and 100 kilopascal. Again, the 298 Kelvin is for the temperature and the 100 kilopascal is for the pressure. These are the standard conditions in which standard enthalpy of neutralization can take place and 1 molecule of water will be successfully produced. Now we can have a reaction that is HNO3 aqueous plus NaOH, that is triazonitrate 5 acid is reacting with sodium hydroxide, all in aqueous form. They will produce sodium triazonitrate 5 salt plus 1 molecule of water. So the heat released when 1 mole of this acid, that is HNO3, reacted with 1 mole of sodium hydroxide to form the 1 mole of the water is what is termed as standard enthalpy of neutralization, but it must be at standard conditions at 298 Kelvin and 100 kilopascal. Note, in neutralization, the real change occurs in the formation of liquid water from the constituent ions. That is, the hydrogen ion is from the acid and the hydroxyl ion is from the base. Now, when 1 mole of this acid, that is hydrogen ion, and 1 mole of the base, which is hydroxyl ion, are reacted at standard conditions, they will produce 1 mole of water. And then the standard enthalpy of solution for this reaction equals to minus 57.3 kilojoules per mole, which means this system is exothermic reaction because there is a negative sign attached to the standard enthalpy of solution. B, the standard enthalpy of neutralization is always negative. It's always negative. That is, whenever you react acid and base, the reaction is always exothermic reaction. That's if you fill the beaker in which you reacted the acid and the base, you find out that the beaker will be warmed. Now we have determination of standard enthalpy of neutralization. These are the steps that you can perform to determine the standard enthalpy of neutralization. A, measure 100 cm cube of 1.0 mole per dm cube HCl and transfer it into a plastic beaker. Here you are using plastic beaker so that in order to minimize the heat loss. B, measure another 100 cm cube of 1.0 mole per dm cube sodium hydroxide and transfer it into another plastic beaker. C, record the initial temperature of the two solutions. That is, you will have T1 and T2. But here the T1 and the T2 will both be initial temperatures. The T1 for the acid and the T2 for the base, or you can say T1 for the base and T2 for the acid. D, transfer the sodium hydroxide into the beaker containing the what? HCl. That is, you add the base to the what? Acid. E, stir the mixture and record the highest temperature reached. That is, stir the mixture and then they record the final temperature. And here we have our specimen results. And our specimen results are volume of HCl is equals to 100 cm cube. As we initially said, 1 cm cube equals to 1 gram. So therefore, 100 cm cube will be equivalent to 100 grams. Volume of sodium hydroxide, that is NaOH, is equal to 100 cm cube, which is also equivalent to 100 grams. Mass of the mixture is equals to 100 plus 100, which is equals to 200 grams. And this mass of the mixture involves both the acid and the base, because each of these acid and the base is equals to 100. So you add these two masses and then you have your 200 grams. Initial temperature of the HCl, that is T1, is equals to 25.1 degrees Celsius. That is the initial temperature of the acid. Again, the initial temperature of the base, which is sodium hydroxide, which is T2, is equals to 24.90 degrees Celsius. We again have the final temperature of the mixture, which is T4, and it is equals to 31.85 degrees Celsius. And then the specific heat capacity of the water is equals to 4.2 joules per mole per Kelvin. Now calculating the standard enthalpy of neutralization. So here we will find the standard enthalpy of neutralization of the water using the acid and the base. We will use the moles of the acid and the moles of the base to know the moles of the water. And then we will calculate the heat involved, and finally we will be able to calculate the standard enthalpy of neutralization. Now we must have a single initial temperature, that is the initial temperature of the HCl and the initial temperature of the sodium hydroxide are added and then divided by 2, so that you will have a single initial temperature. The initial temperature of the acid is 25.1 and that of the base is 24.9. Divided by 2, you will have 25 degrees Celsius. And this 25 degrees Celsius will be our T3. And that T3 will be the initial temperature that we will be using in this reaction. Now, we have rise, or we have temperature rise, that is theta, which is calculated by T4 minus T3, and the T4 is the final temperature and the T3 is the average initial temperature, and these are equal to 31.85 minus 25.0, and then we'll have 6.85 degrees Celsius as our change in temperature. Now let's do the calculations together so that we will have better understanding of what is meant by enthalpy of neutralization. We have solution. Now our temperature rise will be the difference between the final and also the initial temperatures, in which we will have 31.85 minus 25. And then with this, we can use our calculator again and have 31.85 minus 25. And then we will have 6.85 degree Celsius. So this is the what? Temperature rise or change in temperature. So the next thing is to calculate heat evolve, because we know that standard enthalpy of reaction is always exothermic, it's always negative, so we can calculate the heat evolve. And heat evolve is calculated as mc theta. And the m is the mass of the mixture. And the mass of the mixture in this case is 200, because the acid is 100 and the base is 100. We add them, we have 200. And the specific capacity is 4.2 times the theta is the temperature rise, which is 6.85. And then we'll have from the calculator 200 times 4.2 times 6.85. And here we'll have 5754 joules. So this is the amount of energy produced, the amount of heat evolved. Now we'll calculate the mole that has produced this amount of what? Energy, or the mole that has evolved 5,574 joules. Now, from the equation of the reaction, we know that HCl is reacting with sodium hydroxide, and then they will form sodium chloride and also water molecules. So the amount of HCl in the reaction and the amount of sodium hydroxide in the reaction are all equal. Their concentration also are all equal. So therefore, we can either use the HCl or the sodium hydroxide to calculate the mole in this reaction. And if you know the mole of the acid or the mole of the base, we also know the mole of the water. Now, we'll use the formula, which is mole is equals to concentration in, and we go down a bit, we will have mole is equals to concentration in mole per dm cube times volume in cm cube all over 1000. If the volume given was in dm cube, then we will not have divided by 1000. And here we will have the concentration given is 1 mole per dm cube times, and the volume that we use equals to 100 divided by what? 1000. And if you point this in a calculator, you will have something like 0.1 mole. So here we have the mole formula, which equals to concentration in mole per dm cube times volume in cm cube all over 1000. That is, we have 1 for the concentration in mole per dm cube times 100 for the volume of the HCl all over 1000. And at the end, we have 0.1 mole of HCl. We will have the same value if we use the base, because the mole per dm cube, that is the concentration of the base, is 1, and also the volume of the base used in the reaction is 100. So 1 times 100 divided by 1000, you will still have 0.1 mole per dm cube. Now, from the equation of the reaction, we have HCl plus sodium hydroxide is equals to sodium chloride plus water molecule. Now, we will ignore this sodium chloride because water is the major product in this reaction. Now, we have here 1, and here also 1. So, which means we have 1 mole of HCl reacted with 1 mole of sodium hydroxide to produce 1 mole of water. Therefore, we can say 0.1 mole of this acid reacted with what? 0.1 mole of this base, and then they end up forming what? 1 mole, 0.1 mole of the water. So this is the mole of the water in the reaction that has produced this energy. That is, you can say, when calculating the standard enthalpy of neutralization, we can say if 0.1 mole of the water produces 5754 joules. Therefore, 1 mole of the water will produce X joules. And here we can have 0.1 times X is equals to 1 times 5754. We divide both sides by 0.1 to make X the subject of the formula. And here we have X as, we use the calculator to confirm that answer. That is 1 times 5754. But we need to divide it by 0.1 so that we will have 57540 joules. But then we can divide this again by 1000. We put a kilo in order to reduce the value. That is, we have the point after the figure, then we will have 1, 2, 3. At the end, we will have 57.5 kilojoules. When we are discussing about the standard enthalpy of neutralization, we said it is always exothermic reaction, which means we attach what? A negative value. Again, without a negative value, the answer will be wrong. Now, from the screen, we have moles of water produced during the reaction. That is, after calculating the mole of the acid, and then I initially said you can even use the base to calculate the mole. Now we have HCl plus sodium hydroxide, which gave us sodium chloride plus water. Now from the equation of the reaction, 1 mole of HCl reacts with 1 mole of sodium hydroxide to produce or form 1 mole of water. Therefore, 0.1 mole of HCl reacts with 0.1 mole of sodium hydroxide to form 0.1 mole of water. Now we calculate the heat evolved by 1 mole of water, because these standard enthalpies normally take place as standard conditions, and one of the conditions is 1 mole per dm³. That is 1 mole, and the 1 mole here, if you want to find it, you will say 0.1 mole of water will give you 5754 joules of heat. Therefore, 1 mole of water will give you X joules. And if you cross multiply, you will have 1 times 5754 divided by 0.1, which is equals to 57540 joules. And then we divide by 1000 to include the kilo, and then the value will be reduced. But still, this is the same thing. We have 57.4 kilojoules. Hence, the enthalpy of neutralization of HCl by sodium hydroxide is minus 57.5 kilojoules per mole. We include the minus again because the system is exothermic. Now we have our assessment question, and the assessment question reads: in an experiment to determine the heat of neutralization of HCl by sodium hydroxide, 40